Hello and welcome again to another video on number theory. Today's video is about infinitely many primes. Specifically, we're going to talk about a classical result for more than 2000 years ago that is the theorem of Euclid that says that there are infinitely many primes. I mentioned this in the previous video, so this video is exclusively about the proof of this and the numbers, some of the numbers that came out of this theorem. Now, this is the plan for the video lecture. So the first thing I'm going to do is I'm going to tell you a short story about Euclid's proof. I'm going to talk about some technical lemmas, and you will feel free, please, to skip this part because it's actually very technical. Some of the two lemmas that I'm going to talk about here are going to be crucial in the proof of Euclid's theorem, but you can skip the proof of those if that's what you desire. The third part is going to be the Euclid's proof, and the last part is going to be some numbers that are called the Euclid numbers that come or are inspired by the Euclid's proof. Now, I'm going to put the timestamps here and in the video description, so you can go between one and the other depending on what you prefer to watch. So the result of Euclid's theorem appears in the book called Euclid's Elements, and that picture that you see right there is a picture from a book, actual book from the 1400s, which is just, of course, a reprint of that original book, which was, of course, written in Greek. Now, the original book where the theorem came from has 13 chapters, and they call it books, so they say book 1, book 2, and so on. And the proof of the statement is in book 9, proposition 20. And you can see the book online in those pages that you see there. The first one is HTML type of page where you can click and see each individual book and the propositions or the theorems that you have. And the second one is a little bit more interactive, but it only has the first 6 chapters. Now, the links of those web pages, I'm going to put them in the video description. So what was the original statement from Euclid's proof? So the original statement was proposition 20, and it said that prime numbers are more than any assigned multitude of prime numbers, which basically translates to this. If you have a collection of prime numbers, you say you have 10 prime numbers, you can always find an 11th prime number. That's basically what it says. So the original proof, the translated original proof, is about this one. So let's say let A, B, and C the assigned prime numbers. Now, this proof is actually very geometrical. So when Euclid talks about prime numbers, it actually refers to segments, so parts of a line that have a measure of a prime number. Prime segment meaning that you can measure the segment only by the 1 unit, not by 2 units or 3 units. So basically, it's just segments that have length of a prime number. So I say there are more prime numbers than A, B, and C. Now notice that we are talking about 3 particular prime numbers, A, B, and C. This proof will extend to more prime numbers. So basically the proof is you have 3 prime numbers, A, B, and C, and we're going to construct a 4th prime number that is different from A, B, and C. That will prove that the collection of prime numbers is infinite because you can extend the proof to more. For example, if you have 4 segments that are prime numbers, you can construct a 5th and so on. But the original proof of Euclid refers only to 3 prime segments, and then we construct the 4th. So the segments are A, B, and C, which have length of a prime number. And the proof goes like this. Take the least number DE, which is going to be a segment, measured by A, B, and C, and add the unit DF to DE. I will explain what that means. So you take the original segments, A, B, and C, which have prime length, you multiply them together to get a new segment DE, which is what I said, the product of the lengths of A, B, and C, and then you add the unit length to that one. Now the proof of Euclid continues like that, and what happens is from this segment you construct a new prime number. Now the proof does not say that the whole segment is a prime length. It's just that from that segment you're gonna construct a prime number from there, and that's how the original proof of Euclid was. I'm not going to continue looking at all the proof because the point is just to give you sort of an idea of what the original proof was. So this part of the lemmas, the technical lemmas, and then if you are not too keen on looking at very technical things, you are welcome to skip this part. So the first lemma says if I have that A divides B and both A and B are positives, then A is less than or equal to B, meaning that if you number divides another, the divisor is always less than or equal to the dividend here, assuming that A and B are positives. So let's look at the proof. So if we have that A divides B, then we can apply the definition and say that there is an integer k, so that B is a multiple of A. So that's what the definition of divisibility is. Now, the number k must be positive, and the reason for that is because if you look at the numbers A and B here, this is positive, and A is also positive, then k must be positive as well, because if it is not, if k is negative, then that will make B a negative number because A is positive. So k is a positive number, it's a positive integer, and because it's a positive integer, it needs to be bigger than or equal to 1. And that's going to come into place into the proof in a second. So then we have that B is equal to A times K, but A times K is bigger than or equal to A, and that's because of this inequality here. So you basically take this inequality and multiply by A on both sides, so you get AK bigger than or equal to A, and that's what you get right here. And that last statement that it says there is that B is bigger than or equal to the number A, which is the same as A less than or equal to B, and that proves the lemma. So that's the first technical lemma. So basically what you have to take out of this one is when a number A divides a number B, and both of them are positives, then this A is less than or equal to B. It could be equal, but it's always less than or equal. So that will be the end of the proof. Now for the second lemma, and we're going to use these lemmas in the proof of the Euclid theorem, is the following. So if we have a number n that is a natural number bigger than 1, then there is always a prime number p that divides that n. So always when you have any natural number, doesn't matter what the natural number is, there is always a prime number that divides that number. Now this might seem a little bit obvious, but in mathematics you always have to prove all your statements. So let's look at the proof. So we're going to consider two cases. In the case number 1, let's think about n as a prime number, and the case number 2, that is not a prime number. Now n is not 1, -1, and 0, so that means these are the only two cases we have. So let's look at the cases. In the first case, when n is a prime number, it's actually very easy to prove that, because what is a prime divisor of n? N itself. So n divides n because n is a prime number. So we have proof that if you add a prime number, the prime number divides n. So that will take care of that case. Now, of course, the more interesting case is case number 2, in which we have to prove that n has a prime divisor, but n is not a prime number. So that's where the most work of the proof will go. So let's look at case number 2. So let's suppose that n is not a prime number. So what does that mean? That means that n has more than 2 positive divisors, and that's by our definition of prime numbers. A prime number is the one that has exactly 2 positive divisors. So a composite number, or not a prime number, it will be one that has more than 2. So that means that it will have at least 3. Now, one thing that we can immediately say is that n and 1 are both positive divisors of n. Any number n will always have n and 1 as divisors. Because this is not a prime number, that means that there is another divisor, d, that is not 1 and n, that divides the number n. So we have a third positive divisor of n, because it's not a prime number. Now, we're going to use the well-ordering principle to complete the proof. Now, I'm going to put the link in the upper right corner here to the video of the well-ordering principle if you're a little bit rusty about the proof, so you can go and check it out. Now let's look. So when we have the well-ordering principle, we always look at a set. So we're going to take all the natural numbers that are not equal to 1 and n that are divisors of n. So basically what I'm going to do is I'm going to look at all the divisors of n that are not equal to 1 and n. And we're going to take the minimum of that. Now remember, to apply the well-ordering principle, you need to have that A is not empty and A is a subset of n. Now this part, this one, A subset of n, is very clear here from the definition. So we are taking the numbers from the set n. So clearly A is a subset of n. Why is A non-empty? Now the reason for that is because D, remember that divisor of n that is not 1 and n, that is an element of A. So that will make A not empty. So here D, then D is an element of A. So that makes it a not empty set. Now by the well-ordering principle, because we have those two things, non-empty and subset of n, A will have a minimum. So let's call the minimum of A, let's call it D naught. Now the claim is that that is a prime number. Now if we able to prove that D naught is a prime number, then D naught divides n because D naught is in A by the definition of the set A. So the whole proof will rely now on proving that D naught is a prime number. So let's see that. So let's suppose by contradiction that D naught is not a prime number. So if D naught is not a prime number, it means that D naught has a divisor, another divisor, let's call it D1, that is not equal to 1 and D naught, because remember D naught is not prime, so it has more than two divisors, so at least 3. So there's at least one D1 that is not 1 and D0, because these two are always divisors of D naught. So D1 divides D0 and D0 divides n. We already know this one here because D0 is in A. Now one important thing I want to mention here is this one. D1 is in this case strictly less than D0, and the reason for that is because D1 is less than or equal to D0 because of the first lemma we saw, and also because D1 is not equal to D0. Also D0 is strictly less than n. That's because also D0 is a divisor, a proper divisor of n, so it's not 1 or n. Now by transitivity, you can see D1 divides D0 and D0 divides n, so D1 divides n. Now that will prove that D1 is an element of the set A. Why? Because D1 is a natural number. D1 is not 1 or n. Well, D1 is not 1 because of this statement here, and D1 cannot be n because D1 is less than D0 and D0 is less than n. So D1 is strictly less than n, so it cannot be n. And also D1 divides n because of this expression here. Now, I know this could be a little bit more complicated, so if you want, just pause the video here and try to understand what this whole argument is here. So D1 is then in A. And that is a contradiction. Why? Because D0 is the minimum of A, so that's the smallest number in A, but D1 is also in A, so that's what we prove, and D1 is smaller than the smallest number that is in A. That is a contradiction. Now the contradiction came because we assume that D0 is not a prime number, so it is a prime number, so we have found a prime divisor of the number n. So that completes the proof of the second lemma. Now into the proof of Euclid theorem using the lemmas we already proved. So let's look at this one. This is the classical proof that we see in many of the number theory books. This is not exactly the original proof of Euclid. It's an inspiration of that proof. So this is inspired by the Euclid's proof. So let's look at the proof. Now we're going to reason by contradiction, and let's assume there are only finitely many primes. So let's say all the primes are P1, P2, P3, and Pn. So we are assuming that we have n prime numbers. And assuming that we have a finite number of prime numbers, we're going to get to a contradiction. So we're going to look at this number n, which is the product of all the n prime numbers, because we're assuming that is only n of them, and we're going to add 1. Now, if you look at this number right here, n, and you watch the part of the original proof, this is inspired by the original proof. In the original proof, we only had the 3 prime numbers, multiply with it and add 1. In this one, of course, is the n, the first n prime numbers, or the whole prime numbers, P1 through Pn. So we're going to look at that number. By the second lemma, we know that any number has a prime divisor. So that number n that we defined in the previous slide has a prime divisor. But remember that these are all the prime numbers. So that prime divisor has to be one of these that is in this list. So let's say it's, for example, pi. Why pi? It's just a placeholder for any of these primes that could be the prime divisor of n. So it could be any of this. So let's call it pi. So that means that pi divides this number, which is the number n. Why? Because any number has a prime divisor by this lemma number 2. Now, this statement here is not from the lemma, but it's just clear, and I'm going to explain why is that clear. Now, pi appears in this product somewhere over here. That's pi. So pi obviously, of course, divides this because pi is here somewhere in this product. Now, looking at this one and this one right here, so the number or the prime p sub I divides both of them by something what you already saw earlier, is that if a number divides a single number, pi, divides 2 other numbers, it divides any combination of them. So I can say that p sub I divides the subtraction of this one, this number, minus that. But if you notice that if I take this number and subtract that one, I get 1. So that will mean that pi divides 1. And that means that p sub I is less than or equal to 1 by the lemma 1 that we proved. So a divisor is always less than. Pi divides 1, pi has to be less than or equal to 1. And notice that that is a contradiction. And the reason that is a contradiction is because the prime numbers are all bigger than or equal to 2. So that's not possible. You cannot have a prime number less than or equal to 1 because we are talking about positive prime numbers. And that would be the end of the proof. So we have proved that there are infinitely many primes by contradiction. So inspired by that proof, we can define the Euclid numbers, and the n Euclid number is the product of the first n primes plus 1. Now that is the number we use in the proof. Remember that if we assume that there are finitely many primes, we take all the prime numbers from 1 through n and multiply them and add 1. And that number is called the Euclid number. So basically is take all the prime numbers from the first number, second number. So for example, P1 will be 2, P2 will be 3, and so on until the n prime number. Multiply them all and add 1. Now in the Euclid's proof, we don't know if this number is prime or not. It could be prime, it could be not prime. So that's just an Euclid number. So let's do a little bit of computations here. So for example, what it would be E1. So it will be the first prime number. I don't have to multiply any numbers, just the first one, plus 1, so 2 plus 1 is 3. E2 will be the multiplication of the first 2 prime numbers and add 1. So that will be 2 and 3, add 1 to get 7. And E3 will be the multiplication of the first 3 prime numbers add 1. So it will be the 2, 3, and 5. Those are the first 3 prime numbers, add 1. That'll give me 31. And you can continue on like this, of course, to find the Euclid numbers. Now you notice here that 3, 7, and 31, they're prime numbers. It doesn't mean that you're always gonna get a prime number when you compute the Euclid number. Now, this is an important actually question here. It is not known whether En is prime number for an infinite number of values of En. So we don't know if these numbers will give me prime for many values of n. So you can get prime sometimes, and sometimes you don't get a prime number, you get a composite number. So we know that En is prime for n equals 1, 2, and 3, the ones that we saw. Also for 4, 5, 11, and so on until this one right here. Now, checking that this is a prime number is time consuming because these numbers increase in size a lot. So in this list, if you can see here, that means the numbers 7, 8, 6, and for example 10, they're not prime number. That composite. Also 12, 13, and so on, they are not prime numbers until the first one here after that, that is 75. So some of the numbers En are. This statement right here is something that is not known as of now if it is true or not. Do we have infinitely many numbers that for which En is a prime number? That is not known yet. Now we can compute these prime numbers using Pari GP, so the calculator we have. Now the formula for the Euclid number is the product of the first n prime numbers and you add 1. We can translate that into Pari GP by using this command. So if we type in Pari GP E of n, which is the n Euclid number, is going to be the product from I equals 1 to n of the I prime number plus 1. And I will show you that in Pari GP. We can enter the formula for the Euclid numbers in Pari GP as you can see here. So we're going to define in this case will be a new function E of n. So n here is going to be the parameter and this is going to be the product from I equals 1 to n of the ith prime number plus 1. So that will be the formula for the Euclid numbers. Now once you press enter, what's going to happen is the Pari GP is going to say, okay, you defined a function. So that's what all of this means. So a function has as an input, it's going to have an n, and the output is going to be all this formula that we enter right here. So that's going to tell Pari GP how to compute E of n for particular values of n. And in this case, n will be a natural number. So we can find particular values for E of n. So for example, let's say E of, let's say 1. And that will give us the value of E of 1. You can also use, for example, another one, E of 2. And that will give us the value of E of 2. Now, it's not a good idea to type the list of numbers that you want to see. For example, if you want all the E of 1, E of 2 up to E of 10, typing those one by one will take a long time. Now, the good thing is that Pari GP has a way to do this easily by looking at list. So in this case, what we're going to do is we're going to look at list. So let's say we want the list of the first 10 Euclid numbers. So what we do is we open and close a close bracket and we're going to tell Pari GP that we want a list. So the list will be of the numbers E of n. So the type of numbers we want. And we're going to have to tell Pari GP what n's do we want. So we want what kind of n's we want there. Now we're going to use the pipe symbol, and the pipe symbol is going to be right usually above the enter key on your keyboard. And we're going to tell Pari GP what values of n here. So n, let's say, just for an example, we're going to take n from 1 to 10. And to do that, we just type less than or equal sign and the hyphen symbol. So that means n is coming from, and it's coming from the list from 1 to 10 in this case, and that's what we want. So 1 to 10, a list is typed in Pari GP in this way. So 1, 2 dots, and 10. So that will give me the list of all of ENs when n ranges from 1 through 10. So that will give me the 10 Euclid numbers, and that's the 10 Euclid numbers that you see there. Now, the advantage of having something like that is you can change that list to whatever you want. So for example, let's say I want from the 3rd Euclid number to the, let's say, to the 15 Euclid number. So I do a couple of changes and I'm gonna get the list of the Euclid numbers from 3 to 15. So that's a way to do that. Another way to use this type of list that are very powerful in PariGP is we can also ask for what values of n E of n will be a prime number. And we can also ask that from a list. So what do we want? We want a list of all the values of n, and we use the pipe symbol, and we have to tell PariGP the range, in this case, what values of n we want. We want the values of n coming from, let's say, the first 10, that will be 10, the first 10 values of n, but I don't want the values of n alone. I want those for which E of n is a prime number, so I have to specify that for PariGP. There is a function in PariGP that tests if a number is a prime, and that function is called isPrime. So what I want is prime of E of n. So E of n, close parenthesis, and that there is saying this. I'm going to explain what this means. So this is going to be a list of the values of n. The n are going to range from 1 to 10, and you can change this list to whatever list you want, just making sure the first number is always less than the first one. And this is the condition I want. I want the values from 1 through n, so that is prime of n. That is a true value, so that means that it is a prime number. So that should give me the values of n for which E of n is prime. So from 1 to 10, 1, 2, 3, 4, and 5 are prime. So that would mean 6, 7, 8, 9, and 10. Those would be composite numbers for the Euclid number. And you can change the list to whatever you want. So let's say you want the first 20 from n from 1 to 20, and ask which values of n will give me E of n prime. And that will be that list that you see right there. Now, one more thing I want to mention there is, in the list that I gave you, the largest En for which En is a prime number in that list is this one, is E of 33,237. That was one of the numbers that for which En is, and if we press enter, that's going to be a large number. Now, checking that En is a prime number could be difficult because the size of En is going to increase the more you increase the n. So checking for primality will be a little bit harder. So that's how you can use PariGP to play with the Euclid numbers. Okay, so that's all I have to say for today. Thank you for watching. Take care and good luck.